We have so far been talking about stability in the sense of Lyapunov, which for an LTI system concerns only with the A matrix, okay? But we have three other matrices to represent the behavior of the actual system, okay? And in today's lecture, we will talk about the other type of stability, which characterizes which deals with the behavior between the input and the output of the system. Okay, so we're going to study that behavior relationship under the title bounded input, bounded output, or in short, BIBO stability. Okay, so roughly speaking, BIBO stability means that small inputs produce small outputs under the assumption that all the initial conditions are set to 0. So, roughly speaking, bounded input, bounded output stability means small inputs, small in some sense, okay, we're gonna make this expression more precise soon enough, cause small outputs. Okay, under the assumption that all the initial conditions are 0. Okay, that is the initial state, x at t equals 0 is 0. So a rough sketch would mean the following. Suppose that you have here a system represented by some block. Okay, this is our system. With 0 initial conditions. Okay, so you have, let's say, a mass spring system, and you set the initial velocity and initial positions to 0. So the system is at rest, and then what you do is you apply some force, let's say, to that system, and then go and measure what displacement of the mass that force produces. Okay, and you apply all sorts of forces, okay, all sorts of waveforms, and then for all those waveforms you look at you study the output that such waveforms produce, and then by comparing the two sets of inputs and outputs, if you recognize such a general behavior, that is, whenever the magnitudes of the forces irrespective of the waveform of the forces are small, then the output, the displacement waveforms are also small magnitude-wise, then you can say that your mass spring system is bounded input, bounded output stable. Okay. Okay, so suppose that here we have the input entering our system, which is at rest, that is the all initial conditions are 0, and when you excite the system with such input, it produces something at the output, and that's the response of the system due to this input. Now, if the system is bounded input, bounded output stable, so that would mean that, okay, suppose here we have the waveform of the magnitude of the input. Suppose we're dealing with a scalar case, T0, and this is the magnitude of the output. If the input is bounded, that is, the magnitude can always be upper bounded by some fixed border, and such an input produces, for a bounded input bound output stable system, an output that inherits the same property. That is, you can find some constant such that for all future times the magnitude of the output lies below that border. Okay, and then you change your input, but still it's bounded, and then you go and check the output. What you expect is still a bounded output. Okay, and if that's the case, no matter what waveform that you apply from the input, then your system is said to be bound input, bound output, stable. Okay, now let's try to be more quantitative or more precise about this informal definition. For that, let's introduce or let's remember our system. Consider the linear time varying system. Okay, let's call it system 1. X that equals ATX plus BTU, and the output is CTX plus DTU. Okay, the matrices A, B, C, D, they are allowed to be functions of time. X is in Rn, therefore we're talking about an nth order system. U is in Rk, so that means we have k individual inputs in our system, and Y is again a vector of size, let's say n. For this system, the forced response, which was by definition the response due to the input only, okay, or response for zero initial conditions, okay, x t0 equals 0. Okay. For simplicity, let's take our initial time to be 0. Okay. Is what? Y of t, okay, equals, okay, C of t, then we have the state transition matrix T tau B tau U tau D tau. Okay. Now this can be put outside integration because it's just a function of t, whereas integration is with respect to tau. The general expression for the output, note that it also included the term due to, excuse me, you also have dt ut here, okay? Term due to the state, which was Ct times x of t, and x of t was state transition matrix phi t comma 0 multiplying the initial condition x0. But since we're letting the initial condition at t equals 0, okay, to be 0, we don't have that term. And when that term is omitted, what remains is what we're calling the forced response of the system. Okay, so this is the forced response. Okay, and this matrix n by n phi t tau is our state transition matrix, okay, which is a function of the matrix A. Now, let's introduce or let's formalize this definition with this informal definition that is small inputs calls small outputs. Okay, here is our Bible stability definition. System, linear system given by equation 1 is said to be bounded input, bounded output, stable. Okay, or in short, bistable if you can find a constant indicated by G, positive, such that for all input signals, which in general is a vector with k entries, and all those k entries are allowed to be functions of time. So for all input signals, u of t, the force response, which is a vector in Rm, y of t satisfies the following norm condition. Okay, so what you do is you obtain a number by computing, okay, at least in principle, the maximum value that the norm of the response gets. Okay, so this is the supremum, or this just means maximum. Okay, or the limit of maximum. Okay, but for all practical purposes, you can replace this with maximum. So supremum of the norm of y of t throughout the entire time. And then this is a number, and it must be that you should be able to bound this number with this constant g, which is independent of your input choice, u of t. So this is fixed, okay, determined by the system parameters only, a, b, c, d. Okay, and that multiplying the supremum, okay, so the infinite norm of the input signal. Okay, so that's the formal version of our small inputs produce small outputs definition. Okay, now we're not going to spend much time, any time further on the general LTV case. So let's see the implications of this definition on the LTI case. LTI case. Now we're considering the case where the ABCD matrices are constant. AX plus BU, Y equals CX plus DU. Okay, this we call our system 2. X and U and Y, they're of the same size as before. X is in Rn, U is in Rk, and Y is in Rm. Okay, now the force response. Okay, and by definition, we have the system at rest when we apply the input, or in other words, the initial conditions are 0. So the force response for the system is y of t equals the integral c e to the a t minus tau e to the a t being our state transition matrix for the LTI case times b. Then we have u tau d tau, and we also have the term coming from the du piece, dut. Okay, now this term is bounded okay, provided that U of t is bounded because D is a constant matrix. In fact, all our matrices are constant matrices. So that means, when you look at this definition, bounded input, bounded output stability of this system is same as the same system, or almost same system, with D matrix, or the du term omitted, okay, neglected. Or once again, in other words, bounded input, bounded output stability for the LTI case depends only on A, B, and C matrices. It does not depend on the D matrix. So this term is bounded for bounded UT. Okay. So therefore, BIBO stability or lack of it must be determined by, or must be related to, this integral, or more importantly, the integrand here, C times e to the AT times B. So let's therefore look at this term. How about this term? Okay. Now here is our first result that combines this definition of BIBO stability with the integrand of that term that appears in the force response. Theorem system, the LTI system. Okay, our system 2 is BIBO stable if and only if, so it's an equivalence condition, so that provides a complete characterization. Each entry Gij of t of the M by K matrix. Okay, remember, M is the number of our individual outputs, or the size of the output vector, and K is the size of the input vector. Okay, Gij of the M by K matrix C e to the AT times B. Note that the matrix T is left outside the picture because it has nothing to do with bounded input, bound output stability. Is absolutely integrable. Okay. In other words, that is, from 0 to infinity, the absolute value of Gij dt is something bounded, okay, something finite for all entries I, j. Now this is an equivalent condition for BIBO stability, but still it seems hard work to compute all those integrations. Okay, so we have to therefore find if there exists a simpler way to check boundary input, bound output stability for a given LTI system. And for that, all one has to do is to recognize that this matrix of time, okay, which is a function of time, C e to the AT times B, is the inverse Laplace transform of the transfer function matrix for the case when D equals 0, or for the case when D is omitted. Okay, so therefore the transfer function matrix of a system must tell us something, must be closely related to, at least, to bound input, bound output stability of the system. Okay, and that's our next object of this study: how to determine BIBO stability from the transfer function, okay, denoted by G of S of the system. Okay, note that in general, G of S, for a multiple input, multiple output system, G of S is not a scalar, but it's a matrix, okay, of size m by k. M, the number of outputs or the individual outputs, and k is the size of the input vector. Okay, so we have to therefore look at that matrix, transfer function matrix. G of S equals C times Si minus A inverse B plus D. Note that if you take the inverse Laplace transform of this, since the inverse Laplace transform of this middle matrix is e to the at, state transition matrix, this produces C times e to the at B. Okay, and D is just a constant matrix that's being added to that, and or here, and therefore it does not have any effect on the bounded input, bounded output stability of the system. Therefore, you can either study this transfer function of the actual system, or you can ignore this term D and study this reduced transfer function to figure out the properties from the bounded input, bounded output stability point of view. Okay, and here is another condition that's much easier to check than the condition given in our first theorem. Okay, system 2 is bistable if and only if all the poles of all entries of the m by k transfer function matrix G of S are on the open left half plane, okay, are with negative real parts. Okay, so that seems to be a much easier check for bistability than the previous theorem's condition. Okay, so once again, we have for general system with n individual outputs and k individual inputs, the transfer function will be an m by k matrix, and entries of that m by k matrix will be rational functions, okay, some polynomial dividing some other polynomial, and by poles of each of those entries we mean for each of those entries you look at the denominator polynomial, and then the roots of that denominator polynomial is what we're calling the pole of that entry. Okay, so you go entry by entry, you check all the poles, and if all those poles coming from all those entries are with negative real parts, and only then the system is bounded input, bounded output stable. Okay, now we remember, we talked about that before, that the poles of the transfer function are intimately related to the eigenvalues of the A matrix. So that seems to suggest that looking at the eigenvalues of the A matrix may, or sometimes may not, tell us something about the bounded input, bounded output stability of the system. Okay, for that, let's recall the following relation. Okay, set of poles of the transfer function. Okay, so all the poles of the transfer function matrix. Okay, all those numbers, all those points on the complex plane must be a subset, necessarily a subset, and it has to do with this inversion operation. must be the subset of the eigenvalues of the A matrix. Okay. Set of eigenvalues of A matrix. Okay. Therefore, if we check the eigenvalues of A matrix, and if all of them are with strict negative real parts, then without having to compute the transfer function matrix, we would know for sure that all the poles must have negative real parts. And as a result, the system is bounded input, bound output, stable. So that produces not an if and only if condition, it just produces a sufficient condition for bound input, bound output stability. Namely, check the eigenvalues of the A matrix. If all of them are on the open left half plane, then your system is bound input, bound output stable. But if your A matrix has some poles on the imaginary axis or on the right half plane, okay, open right half plane, then your system may or may not be bound input, bound output stable. Okay, so that's therefore only a sufficient condition. So let's formalize that in our next theorem. If our LTI system is exponentially stable in the sense of Lyapunov, okay, or if all the eigenvalues are with negative real parts, then it is Bibo stable. Okay, but as we just said, the reverse direction is not in general true. The converse statement is not true in general. Okay, so let's see an example that has to do with the last two theorems. Okay, consider the following second order system, which we will study from the bounded input, bound output stability point of view. Okay, consider x that equals 0, 1, 6, minus 1x plus 1 minus 3 u. So those are our A and B matrices, and y equals 1, 0, x. Namely, output is the first state variable, x1, and plus 0 times, so therefore we have no D matrix, or the D matrix is 0. Okay, so this is our A, this is our B, and this is our C. So let's therefore figure out whether this system is bounded input, bound output stable or not. An easy check or easy first step seems to be that we can use this theorem. That is, we can figure out the eigenvalues of the A matrix, which is very easy because it's just a 2 by 2 matrix. If all of them are with strict negative real parts, then we can stop there. This system must be bound input, bound output stable. If it's not, then we have to go one step further and compute the transfer function and check the pole locations. So let's figure out the eigenvalues of our A matrix therefore. Eigenvalues of A matrix. Okay, the characteristic polynomial s minus 1 minus 6s plus 1 is s plus 1 minus 6. That's s squared plus s minus 6. And that's s plus 3, s minus 2. So we have a pair of real eigenvalues. One at minus 3, okay, negative real part. The other is at 2, positive. So that's an unstable eigenvalue. So we cannot therefore immediately conclude that this system is bound input, bound output stable. So we have to go and check the transfer function. So lambda 1, 2 are at 2 and minus 3. Now due to lambda 1 equals 2, which is only open right half plane, system is unstable. Okay, in the sense of Lyapunov. Now, how about Bible stability? Okay, for that, what we do is we move further and compute the transfer function. So let's do that. G of s equals CSI minus A inverse times B plus D. Now in our case, D equals 0. And SI minus A inverse equals, here we have SI minus A, and here we have the determinant of SI minus A. Therefore, we can simply write 1 over S plus 3, S minus 2, okay, 1 over the determinant times, okay, swap the diagonal terms and negate the anti-diagonal terms. So that's our SI minus A inverse. Okay, multiplying that matrix from left and right by C and B respectively, that will give us the transfer function. So let's do that. So we have transfer function equals C multiplying S plus 1, 1, 6, S, and then here we have B. And everything is divided by the characteristic polynomial. S plus 3, S minus 2. And since everything is divided by this characteristic polynomial, the set of poles of the transfer function must be a subset of the eigenvalues of the A matrix, because the roots of this characteristic polynomial are by definition the eigenvalues of the A matrix. Now, here we have S minus 2 term, and it's dividing everything. And therefore, what we expect is we expect a pole at S minus 2. Okay? So that we expect, therefore, that if the system is not stable in the sense of Lyapunov, it cannot be stable also in the sense of bound input, bound output stability. But it turns out that sometimes here in the numerator there is a term that matches this unwanted terms, and we would have the so-called pole zero cancellations. So even though we seem to have an unstable term in the denominator, that's cancelled by the same term in the numerator, and the overall net transfer function does not display that harmful eigenvalue. And as a result, an unstable system may have a bound input, bound output stable characteristic. So let's keep on computing G of S. Okay. Therefore, G of S equals, okay, this C will pick the first row, and this first row times the B matrix is S plus 1 minus 3. S plus 1 minus 3 is S minus 2. So here we have S minus 2. And the denominator is S plus 3, S minus 2. Okay? So, when that's the case, we don't leave the transfer function. As such, what we do is we do all the cancellations that we can. For instance, S minus 2 here and S minus 2 here. So what we have here, therefore, is 1 over S plus 3. So for a second order system, we obtain a first order transfer function. And that means that somewhere there had been a pole zero cancellation. Okay, and no pole zero cancellation would mean the order of the transfer function, the order of the system will be equal. Okay, now once we have the transfer function, we can exactly say whether the system is bounded input bound up stable or not. So what are the poles of the transfer function, g of s? This is the transfer function after the elimination, and then we look at the denominator polynomial, which is of order 1. Its root is at minus 3. Therefore, all the roots, all the poles, in fact, we have just one pole, but all the poles are with negative real parts. Therefore, by our recent theorem, the system is bound input, bound output stable, despite the fact that it's not stable in the sense of Lyapunov. Okay, G of S has a single pole, and it's at S equals minus 3, which is clearly negative. Okay. Therefore, the system is viable, stable. That is, if you set all the initial conditions to 0 of your system and excite the system with your favorite bounded input, you will always receive a bounded response at the output. Okay. Now, this pole zero cancellation has to do with, indirectly, the fact that has the fact that this B matrix, okay, in this case it's just a vector 1 minus 3, is the eigenvector. I'm talking about the A matrix eigenvector corresponding to the stable eigenvalue at minus 3. So when that is the case, we have some sort of so-called uncontrollability in our system, and this pole zero cancellation business is very close related to unobservability and or uncontrollability. Okay, and starting from our next lecture, we will begin to talk about those very important two subjects related to systems theory, namely controllability and then later on observability.